Welcome to our Lesson 8 lecture. Lesson 8, we're talking about sources and sinks and fields. We've already talked about this last chapter, but now we're going to look at different ways we can find net flow along or across. So starting here with a given field Mn, first thing we look at is formulas for the divergence of the field and rotation of the field. So we abbreviate that as div field and rot field, but again, we want to read them as what they are. So div field is the divergence of the field. The equation for that is the derivative with respect to x of m plus the derivative with respect to y of n. And the rotation of the field is almost kind of the same. It's the derivative with respect to x of n minus the derivative with respect to y of m. So obviously, in the first one, you could switch them. You have 2 plus 3 equals 3 plus 2. But the second one, you cannot switch. Okay, the derivative with respect to x of n has to come first. All right, so to calculate the net flow of a vector field across a boundary C of a region R, last chapter we used this integral. Okay, and the integral always works. It's just sometimes it's not the easiest route. Okay, in this chapter, there's another way we can do this. It's by using a double integral over the region R of the divergence of the field. It could be dy dx or dx dy, doesn't matter. As long as there are no singularities inside the region R. If there are, we have to divert back to the first integral. All right, so if the divergence of the field is positive at a given point, then that point is known as a source. If you circle that point, if you put a small circle around that point, the net flow across would be in to out. If the divergence of the field is negative, that point would then be a sink, and if you put a small circle around that point, the net flow would be out to in. To detect a source or a sink at a similarity, you center a small circle of radius r at the singularity, and you calculate this limit. Like I said, if there's a singularity, we can't use the divergence of the field. We have to go back to this formula that you've already been using. Okay, an important note there. N times dx is not the same as the derivative with respect to x of n. I know it seems obvious, but it's a mistake that some students make, so just keep that in mind. Okay, so then reading on there, if a limit has a positive value, you've located a singularity source. If the limit has a negative value, you've located a singularity sink. If the limit has no value, 0, you've located a singularity as neither a source or sink. All right, next part here, calculate net flow along the boundary C of a region R. Last chapter, we used this. Integral. But there's another integral that works as long as there's no singularity, and sometimes it can be a whole lot easier. It's a double integral over the region R of the rotation of the field. Again, it's provided there is no singularities. Okay, so recall the formula for the rotation of the field is the derivative with respect to x of n times minus the derivative with respect to y of m, which is very close to part 2 of the gradient test, right? So let's take a look at the gradient test. The gradient test says, all right, well, there has to be no singularities. That's part 1. And part 2 says the derivative with respect to y of m minus the derivative with respect to x of n must equal 0. All right, so since they're so closely related here, we can say that every gradient field must have 0 swirl. So if there's a singularity, we calculate the net flow of the field along a small circle centered at that singularity. If the net flow of the field along the curve is not zero, then that field simply is not a gradient field. Okay, for an incompressible fluid flow like water flow, the net flow across any closed curve C without loops must be zero unless there are sources or sinks inside C. Just think about that realistically. It makes sense, you know, if you had water flowing across a circle there, whatever goes in must also go out, unless there's a drain inside the circle or a source inside the circle. Okay? I'm not going to read that part 2. You can read that on your own. Let's skip down to here. We have two curves here. Given functions m and n, what do you check to be sure that these two integrals are equal without going through all the trouble to make calculations? Okay? So there's two things that you're going to check. Obviously, you have to make sure there's no singularities between the two. So no singularities between C1 and C2. If there's one inside of C1, inside of C2, which then would also be inside of C1, that's fine. Or if there's one outside of both of them, that's fine as well. But as long as there's not any between the two. Okay, and then also you have to make sure that all points between C1 and C2 have a rotation of the field of 0. If those two things are true, we would know that the integral across C1 and the integral across C2 would be the same. All right, so the last 2 pages here are just 4 practice problems that I got. So we have a field, and we have a closed curve, and we have an interval. And then it asks us for flow across. And as soon as you flow across, you're thinking, all right, I want to try to use div field here, divergence of the field, if I can. It'd be a whole lot easier. So let's take the divergence of this field and see what we get, because there's no singularities. So I can use this. So the divergence of the field would be 7 plus 1, which is 8, which is going to make this really easy to do. So our double integral, it doesn't even matter what our bounds are, double integral of 8 is always going to be positive. All right? So this question isn't specifically asking for what is the net flow. It's just asking is the flow in to out or out to in. So since we know this is going to be positive, we can say the net flow of field across the curve must be from inside to outside. Really, no work necessary. So much less work than would have been had we went through our other way of integrating this. Okay, now if it asks us for the actual value, yeah, this would still be a good amount of work. Okay, but it's not asking for the actual value. It's just asking for in to out or out to in. Number 2, now we're looking for the flow along a curve. So as soon as you see that, you're thinking rotation of the field. And again, it's just asking is it clockwise or counterclockwise. So there's no singularities in that field. Let's check the rotation of the field. And we would get negative 6x squared minus 5y to the 4th, which if I take out a negative, I get this. And it should be fairly obvious that what's inside the parentheses would always be positive, except at 0, 0. It would be 0 then. And since we have negative out in front, this expression would always be negative. Again, except at 0, 0. But at 0, 0 it would be 0, so that's not really going to change anything. Okay, so that means if we took the double integral of this expression, no matter what our bounds were, it would also be negative. which tells us the net flow of this field along the curve must be clockwise. Saving a lot of time using the divergence of the field and the rotation of the field formulas. Number 3 says we have a new field here, and C is going to be a rectangle this time. Measure the net flow of the vector field across the curve. All right, so we see across the curve there. We know we're going to be using divergence of the field. So let's take our divergence of the field formula. 2x minus 4y. Unfortunately, this is not always positive or always negative. So we cannot just say, all right, well, it's going to always be positive or always be negative. We know the answer. We actually have to calculate this. Okay, so we're going to take the double integral over the region R of the divergence of the field. And we'll see what we get back. Okay, so let's take a look at our double integral here. Our x bounds are negative 2 to 5. Our y bounds are negative 1 to 4. And our div field is 2x minus 4y. And then we're just going to go ahead and calculate that double integral. Remember, first we're integrating with respect to y. All right, so if we substitute 4 in for y, we get 8x minus 32. If we substitute negative 1 in for y, we would get negative 2x minus 2. All right, let's simplify that a little bit first here before we do anything further. 8x plus 2x is 10x. Negative 32 plus 2 is negative 30. And now integrating that with respect to x, we get 5x squared minus 30x. All right, substituting 5 in there, we get 125 minus 150. Substituting negative 2 in there, we get 20 plus 60. And if you add that all up, you should get negative 105, which is negative, which is the important number there. So that tells us that the net flow of this field across that rectangle that was given to us is outside and inside, or against our normal vectors. All right, so last one here, number 4, we have a field and a curve. Measure the net flow along the curve, so you're immediately thinking rotation of the field, raw field. Unfortunately, should be really obvious that there is a singularity in this field. So we cannot use the rotation of the field. We got to go back to what we learned last chapter. Okay? So we're going to set up this integral instead. Integral from 0 to 2 pi of m dx plus n dy. Okay, and maybe we should get those here first. We know, well, we already know x is cosine. We know y is sine. So then x prime is negative sine, y prime is cosine. All right, let's just substitute all that in and see what we get. So we have negative sine t over, well, I mean, this is going to be cosine squared plus sine squared, which is great. Times dx, which is negative sine t, plus cosine t over, again, cosine squared plus sine squared, which is, again, great, times dy. dt. So doing some quick simplifying here, we end up with negative times negative is a positive, sine squared over 1 plus cosine squared over 1. It's great how things work out like that. And then we end up with just 1. So our integral then would just be t from 0 to 2 pi. So it's 2 pi minus 0 or 2 pi. Which then tells us that, finally, the net flow of this field along this curve is counterclockwise, or with our tangent vectors. And that is it for our Chapter 8, Lesson 8 lecture. If you have any questions, as always, let me know.